Hello, in this video I'm going to talk about applications of radian measure. So usually when we talk about applications of a radian measure, we're talking about the arc length, which in this case is given by the formula S equals R times theta. Now to kind of get a better idea of like what that might look like, let's just draw like a circle and let's go ahead and say, for example, that we find the center and we want to draw like a line that represents both the radius, so right here, let's just do that. Okay, so let's say that this has radius r and that has radius r, and then let's say that, for example, that we want to label uh, the value s. Now s is basically just going to be the measure of the curve from where the ray intersects the circle, so like right here and right here. But you also have, for example, that the value of the angle would have to be indicated as so. So like let's just say that that's theta. Well, in this case, like, if this was 90 degrees, then theta would be 90 degrees, but in radians. So that's one thing that you'll need to put is that theta is in radians. Okay? Now, interestingly enough, like for example, let's say that you wanted to know the measure of the arc if you were going to rotate 360 degrees. Well, if you were going to do that, that would mean that you would have 360 degrees, but of course you need that to be in radians, so that's going to be 2 pi radians. So that means that S is equal to, well, that's just going to be, let's see, well, that's going to be R times 2 pi, which is the same thing as 2 pi r. Now think of it this way. 2 pi r in actuality is known as the circumference of a circle with radius r. So in that case, it kind of works itself out in terms of like, in what way can you kind of relate the arc length? Well, in this case, it's the same thing as thinking of it as the circumference. Now, let's go ahead and consider an example, for instance, where we have that we're going to use um, that you have, let's say, a radius. So suppose that you have a circle, and let's say that that circle, it has its own radius, which in this case will be 25.60 centimeters. Okay, now we'll go ahead and use that, for instance, that we want to know what is the measure of the arc if we have that, for example, that A is going to be that theta is 7 pi 8 radians, and that for part B, we'll say that theta is 54 degrees. Okay, now for these, it's very likely that you'll need a calculator. Let's just move this a little because I need some room. Okay, now let's go ahead and say that we work out part A. Now, part A already basically has everything that you need. You have that S equals to R times theta, but what is R? R is 25.6 centimeters, so that's going to be multiplied by 7 pi over 8. Now, in this case, if we go ahead and we multiply through, that should give us what we want. So let's go ahead and use our calculator where we have that you'll take 25.60 And let's multiply that times the 7/8. So if we do that, we get 22.4. Okay, so this is approximately equal to 22.4 pi. Now the units in this case is going to be centimeters because you have that it's in centimeters. So, and you can think about the dimensional analysis that happened because basically you do have that for your radius 25.6 centimeters. That's actually equal to 1 radian. Okay, now if we go ahead and we figure out like what this is in terms of an approximation, let's go ahead and say that we're going to round to 2 decimal places. So that's going to be 70, 70.37 centimeters. So both of these are acceptable, which in either case, most of the time you're told like how many decimal places that you need to round. So if you look at part B, well, part B is a little different because basically you have that it's not in radians yet. So you have to convert it. So take your theta, your 54 degrees, multiply by pi over 180. Now, if you want, you can actually reduce this if you wanted to. So, for example, like 54 divided by 180. But then what you can do is probably just say math frac. Let's see if this works. Okay, so 3/10 pi. Okay, so this is going to be 3 over 10 pi. Now, basically, you're going to do the exact same thing. You're going to say that you'll take the 25.60 and you're going to multiply by 3/10 pi. Now, if you go ahead and you write the symbolic answer, basically you just need to take the 3/10 and multiply by the 25.60 centimeters, and you get 7.68 pi. Okay, so 7.68 pi, and that's centimeters. Or, okay, so or, because you can give an approximation. So times, and notice that I'm using the stored pi, not the estimated pi. So that's going to be 24.13 if we round to the second decimal place. So we have 24.13 centimeters, and that's our answer. Okay. Now, let's say that we look at another example where we want to find the kind of like the arc length essentially, because in this case you have a pulley which it lifts a weight. So basically this pulley is rotating, and as it rotates it lifts it up. Now in that case that's going to be the measure of the arc in terms of like as it rotates. So we want to know like how many inches this pulley is going to be raised. So let's go ahead and do it like this. So in this example, we'll look at part A and we'll say that theta is equal to 71 degrees and 50 minutes. But notice that basically you have that this is in minutes, so we should probably convert that before moving on. So I know that I'm going to take the 50 minutes and I'm going to divide that by 60. Okay, now that's going to be plus the 71, so 71. But this is in degrees, okay? So let's say that you go ahead and you write it as a fraction, which you can, which is 431 over 6. So first off, this equals to 431 over 6 degrees. But remember that I can convert that by taking 431, divide by 6, multiply by pi over 180. Now, in this case, it's probably best that we just leave it as so, because essentially we're just looking for an approximation. So if you want to do that, you can. So like, you can just say like 180 times 6, um, which if you want to try to see if it reduces, you can. Okay, so, and then of course you can try to ask it to reduce it, which it didn't. Okay, so this equals to 431 over 1080 pi. Okay, so yeah. So what we want to do next is essentially just say, well, if we go ahead and we now know the measure of the radius, well, we already did, so 9.27 inches. Now that's going to be multiplied by 431 pi divided by 1080. Now, you can probably try to preserve, like the symbol pi, but let's go ahead and just round this to the nearest tenth. So let's go ahead and go back to the calculator. Now, notice that I already have it stored, so, let's just take the pi, multiply it through. Okay, so this is the radian measure, technically. We're going to multiply that by 9.27, and then we're going to hit enter. So it looks like this pulley is raised about 11.6 inches. So we have 11.6 inches. Okay. Now, let's say that, for example, that you wanted to work that last question. So that last question, basically what's being asked is that it wants to know how much you should rotate so that the arc is going to be 6 inches. So we'll go ahead and say that we know what S is. It's equal to 6 inches. So what you'll do is you'll take 6, you'll set it equal to, not 2, but 9.27, right? Okay, so 9.27, and that's times theta. Now, in this case, and it says to the nearest minute, by the way. So in this case, like you have that theta is going to be 6 divided by 9.27. Now notice that this is in radians, okay? So this is in radians. So in that case, we can convert this into degrees. So what we're going to do is we're just going to say we have theta equals to 6 divided by 9.27 multiplied by your pi over 180. Now in this case, I don't need to simplify at all because I know that I'm just looking for the nearest minute. So what I'll do is I'll take 6 divided by 9.27. Okay, so this is the radian measure. Okay, so I'm going to multiply that by, by pi, and that's divided by 180. Oh, wait. Actually, yeah, I just noticed that it's times 180. Yeah. Times 180 divided by pi, because the radians have to cancel out. Let's just do this. Okay. Alright, so that's going to be 37.08, but remember that it's to the nearest minute, so let's just peel away the 37 and then just multiply by 60. And to the nearest minute, that's basically 5 minutes essentially. So you have that it's going to be 37 degrees. And 5 minutes. Which I guess this kind of makes sense given that um, the previous example, it was almost twice it. So I guess that kind of makes sense, especially because like see like how there is kind of like almost like close, really close, but not, it's just off by a little bit. Now, this next example is pretty much like a classic example of figuring out, like as one gear rotates, the other rotates as well. So two gears are adjusted so that the smaller gear drives the larger one, as shown in the figure. If the smaller one rotates through an angle of 300 degrees, how many degrees does the larger gear rotate? So essentially, you have to break it down into you have that there's uh, a measure that you know is S, so it's the measure of the arc, and then you have S2 is equal to R1, not R1, but R theta, or R2, and then theta 2. The only thing though is that if the little one moves, then this one moves too, the same amount. So in that case, that means that both these two have to be equal. So, so really it's just notation to be honest. So I know that I'm gonna have 3.7, and then I know that it's multiplied by 300, but let's just multiply that by pi over 180. Um, and then this is equal to 7.1 uh, multiplied by theta 2. Okay. Now it's kind of weird because if I think of it like this, all that I really technically need to do is just divide the 7.1 into the 3.7 and then multiply by the 300 degrees, and then that's it. Mostly because the question's asking how many degrees does the larger gear rotate, meaning that if I multiply or if I convert it back to degrees, then it's like I'm just undoing what's being done, if that makes sense. So using some manipulation, we have 3.7 divided by 7.1 multiplied by 300 multiplied by pi over 180. But remember how I was saying you're going to have to multiply by uh, the 180 over pi anyways. So you have 180 over pi. But essentially everything is just going to cancel out. Uh, in reality, you know that the dimensions cancels out to where you're ending up with degrees anyways. Okay, so it's just preference, to be honest. Okay, so if we take 3.7 divided by 7.1, and we multiply this by, we can multiply this by 300, and we get 156. So if we round to the nearest degree, it's 156 degrees. So just to clarify, you have that the pi canceled out, the 180 canceled out, and then see over here, you have that that's a degree right there. Okay, so in this case, like we do have that the dimensions kind of like work itself out in this case. So we have that this is going to be approximately 156 degrees. And that kind of makes sense that the gear to ratio, you have that if this one moves more, this one moves like kind of like proportional. So like in this case, you have that this moved like half of it in this sense, especially because you have that the radius is twice as large, almost, but not necessarily. Now, in an exam, I suppose that, yeah, you might actually have to reduce the 300 degrees Because remember how like when you convert 300 degrees to radians, you're multiplying by the pi over 180, and you have that that's the radian. So then in that case, this is going to be, let's see, probably 5 pi over 3. Um, yeah, 5 pi over 3 radians. But remember how, like, if you're gonna go ahead and multiply this through, the algebra works itself out regardless. So if you really were a purist where you're like, okay, but I'm used to just saying 3.7 divided by 7.1 multiplied by 5 pi over 3. So in this case, you would have been still multiplying by the 180 divided by pi, but you can see that basically the algebra works itself out to where everything else just cancels out into just saying that you're taking the ratio, the 3.7 divided by 7.1, and you're just multiplying that times the 300 degrees, which in this case, it kind of works itself out in terms of the dimensions. So it gives you the same thing basically. So yeah, but I was just showing you that sometimes you do have to show at least the algebra that you took to find the second angle first, or in this case the first angle, which was 5 pi over 3 radians. Now this last part is about area of a sector. So let's say that we go back to our circle, and let's say that we have something like this. Now, in this case, okay, so yeah, that's still S is for the curve, and then you still have that this is R and this is R. Now, the thing of which that we do happen to know is that the area, traditionally the area of a circle is equal to pi r squared. Now, if we were to kind of think about it with regard to, like the fraction of the area, so this is like just like a fraction of the area. So we can say it like this, like, okay, so if this angle measure is theta, then I know that theta is going to be just a fraction of, actually, yeah, let's do it like this. Let's just take that theta is divided by 2 pi. That actually works out. So in this case, this is like a short amount of the full area. So in that case, I'm going to multiply this amount by pi r squared, because then in that case, that's going to tell us that the area of the sector, which I'll use like a little script A, and that's equal to, okay, so theta divided by 2 pi multiplied by pi r squared, which in this case we end up with, let's see, okay, so the pi's cancels out and you're left with 1/2 theta, well, let's do it like this, 1/2 r squared times theta. So the formula for the area of a sector is 1/2 r squared times theta. But remember that theta is in radians. Okay, so that means that, you have to remember that, if you are going to have to convert, then just go ahead and convert it as needed. Now, let's go ahead and do like an example of finding the area. Okay, so if we go ahead and we try to find the area of a sector, let's say that, for example, that you have that theta is 135 degrees, and you have that r is equal to 40 miles. Now, in this case, you know, the best that we can probably do here is try to sketch it. So for instance, like if you draw like a circle and you have that you know its center point, and then the central angle is 135 degrees. So basically that means that the angle looks something like this. So our region, and yeah, this is not really the best sketch. So we have that the radius, which was given as 40 miles, is as so. Now, in this case, all that we got to do is just convert the theta into radians. So take 135, multiply by pi over 180. Now, basically, you have that 135. This has a common factor of 45. So we have 45 times 3 times pi divided by 45 times 4. So we get rid of the 45s and you are left with that the measurement in radians is 3 pi over 4. So that's your radians. Now the area of the sector in this case is equal to take 1/2 multiplied by your r, so that's going to be 40 squared, but multiplied by 3 pi over 4. Now, what you want to do next is, let's go ahead and divide, or multiply by half. Actually, this is not good. Let's just say 0.5 times 40 squared, multiplied by 3 pi over 4. And we're just going to do that. Okay, so in this case, let's see, we're going to round to okay, yeah. So we're going to round to the nearest square foot. So that's going to be approximately 1,895. Wait, that's not right. I put too much. 885. Yeah. And that's going to be squared miles. And that's it. So, area of a sector just requires that you just substitute the r and the theta. Now, if theta was already given, then there wouldn't be too much to do in any case. So, like for example, if you had that that you wanted to try an example, try like for example, if you have that r is equal to 30 inches, and then let's say that theta is equal to pi over 2. That's actually a little more easy in this case. Like if you were to think of, okay, well, I have a circle and its like radius is 90 degrees, and you're just gonna say, okay, well, you have this amount, and this is going to be the shaded region. I went out a little bit. Now, if you think about it, the area is really just, pi r squared. But in this case, it's only a quarter of it. So it kind of works itself out if you do it this way. Because check this out. The area is just going to be 1/2 multiplied by the radius squared, but then multiplied by pi over 2, which in any case, this is pi times 30 squared divided by 4, which is still consistent with the way that I drew it, where I have that this just represents a quarter of it. But of course, the whole point of this example is that you find the approximation in this case. So go ahead and finish this computation and see like what you get. You can probably just round to the nearest tenth for this one. Okay. Okay, so that's going to be it for this video. In the next section, we're going to look at the unit circle. So in any case, we're going to view our trigonometric functions as it relates to a circle with radius 1, of which in either case, you're going to be seeing this a lot from now until basically calculus 2 almost, maybe even cal 3. So, the next section is actually going to be pretty important, and I'm going to actually uh, have you look at it, the unit circle, and be able to fill it out entirely, whether it's based on memory or just, kind of converting and things like that. Okay.